Okay, our next speakers, Krzysztof Narkowicz and Tiago Costa from Epic Games. Krzysztof is an engineering fellow in graphics at Epic Games, where he co-founded Lumen and works on lighting. Prior to that, he spent over a decade working on smaller game titles at 11-bit studios and Flying Wild Hog. He loves working with artists, pretty pixels, and coding close to the metal. Tiago Costa is a principal rendering programmer at Epic Games, working on ray tracing and other rendering features. Previously, he worked at Rockstar North, Apple, and Meta Reality Labs. Here you go.
Hi, my name is Krzysztof, and together with Tiago Costa, we'd like to present our new stochastic direct lighting technique in Unreal Engine 5. We're going to keep this somewhat high level, but later you'll be able to find all the details inside published slides. Games constantly want to push the quality bar. They want to use more lights. They want all lights to be fully dynamic and shadow casting. They want to use area lights with nice soft shadows. And they also want to use more complex BRDFs, material layering, where getting to the point where basically just unshadowed light evaluation can become too expensive. Also, games are becoming more complex. I think we are now at the point where actually workflows are the main limiting factor of game graphics. Ideally, artists should be able to work playfully without many limitations, just like on this screenshot here, which is maybe a bit too excessive, but well, this is what happened when they figured out how to procedurally place lights. We also want this to be our baseline lighting method, something where the production can target, instead of being this extra method which they have specifically relied for. So this has to work at least on consoles and mid-range PCs. And there are many ways how we can approach direct lighting. In games, we usually use forward or deferred lighting, where first for each light we pre-compute a shadow map, or maybe we ray trace shadows, denoise them, and pre-compute a shadow mask. And then we multiply this shadow term by the pre-integrated light irradiance. And this works pretty well for a small number of light sources, but as the number of lights increases, this can get too expensive. Another approach, which is more common in offline rendering, is to trace a fixed number of rays, let's say based on the BRDF, or maybe towards some subset of lights. And if the ray hits the light, then we accumulate that energy. And this scales really well, because now, no matter how many light sources are there in the scene, we are always doing this fixed amount of work. Now, given how popular deferred lighting is in games, this is where we started our investigation. We tried a bunch of different techniques, but nothing really could scale to our desired lighting complexity. And when we carefully looked at our content, it was obvious why. So for example, if we look at this pixel here, it's in attenuation range of 50 lights. So we have to pre-compute 50 shadow maps, but only 15 lights are actually visible. So we just did a lot of wasted work. And even if we look at those visible lights, 80% of the energy is just coming from one light. So why are we even trying to compute all those 50 lights? It's really enough just to compute this one light at full quality and do some kind of approximation for the rest. The other approach is BRDF sampling, which is basically, let's make it a GI problem. It's a pretty common approach. It's a pretty common workaround in Unreal Engine, where artists take some kind of emissive meshes, they hide them from the main view, and they essentially use them as soft area light sources. It's free, because anyway we have to compute the GI, but it has certain quality issues. When we are doing this BRDF sampling, even with some additional guiding from the GI, it's still really hard to find those emissive surfaces, especially if they are very small or maybe they are far away. And another problem is that GI is already hard. Even in offline rendering, it's common to use tricks like placing lights inside windows so that GI can converge faster. But here we have this GI, which has to work on consoles at 60 Hz, and we are adding an extra problem on top of it. The third approach would be to build a new system, where we stochastically would trace a fixed number of rays, towards some stochastically selected subset of lights. And if a ray hits a light, then we accumulate that energy into a single render target. And after all tracing is done, we are going to denoise this render target. And this scales really well, because no matter how many lights are there in the scene, we are always doing this fixed amount of work. Now, obviously, in practice, things aren't that simple. On a console, we can maybe do like 1 ray per pixel, which means that the light selection is extremely critical here. If we take a look at this diagram here, we just trace 2 rays towards 2 lights. They seem to be really important because they're really close. But turns out that all those lights are occluded, and we just wasted our entire tracing budget, and we didn't really compute anything. There are a few different ways how we can approach light selection. A pretty popular one are light hierarchies, where first we put all our lights into some kind of hierarchy, and then we try to find the most interesting cluster. And they all have the same problem. They don't account for this shadowing term, which, as we can see here, is really important. The other very popular approach is Restir. I think everyone saw how amazing stuff it can ship on a high-end PC GPU. But the question is, can it scale down? Can it become this our baseline lighting method? And in order to answer this question, we actually need to take a look at what Restir does. So it would inject those 3 orange blocks into our previous pipeline, and those blocks will first try to grab some samples from the history, or maybe from the neighborhood. Then we are going to trace a ray in order to check the visibility of those reused samples. And finally, we are going to combine reused samples together with the stochastically selected light candidates. And the general idea here, if this frame, we select some really bad candidates, let's say all our selected lights are occluded, then most likely we can find something better in the history, or maybe our neighbors were more lucky. And this works really well for the quality side, but it also adds a very high constant cost. And it's not only the cost of the reuse, but reuse operation, but most importantly, it's the cost of those extra traces. Because now we need to check the visibility of each reused sample. In order to get reasonable quality, we need to do at least like 1 sample per pixel, which would require tracing 2 or 3 rays per pixel here. But on a console, we can do maybe 1 trace per pixel. The other problem is candidate sampling. So in theory, we could just grab a random light from the list and be done, but in practice, to get a reasonable quality, we need to be really careful with our light selection. We need to weight each light by the brdf, and we need to check at least 20% of the light list. And this is maybe not a big deal on a high-end PC GPU, but on a console, it can get really expensive. Because basically what we are doing here, we are doing unshadowed light evaluation for 20% of lights in our scene. And it's even more problematic when we have strong occluded lights. Because we weight each light by the brdf, we are going to trace a bunch of those candidate samples towards those lights, making it even harder to find those visible high-quality candidate samples. So basically, Restir is already outside of our budget, and we kind of still need to solve a very similar light sampling problem as before. So a good question is there something what we can do better than Restir? And when we were playing with stochastic light sampling, we noticed that sometimes simple sampling without any kind of reuse looks better than Restir. And there is a very good explanation for that. So what Restir does, it reuses good discrete samples from the history. But this causes sample correlation. Basically, on the output, we get those clumps of samples, which are really hard to denoise. Ideally, what we would have here is that we would have a visible light list per pixel, so that each frame we can select a different light from the list and generate those nice interleaved patterns, which are really easy to denoise. And this has to be a visible light list. We don't want to be tracing towards occluded lights. They don't really contribute towards final pixels. And likely samples which were visible last frame will be also visible this frame, so we can use history to build this visible light list. Now, we cannot build a light list per pixel. That would be just too much data. But we could have it for, let's say, 8x8 screen space style. And now, when we have this light list, during sampling, we can take our pixel, reproject it into the previous frame, and pick a light from that list. Those 8 by 8 screen space tiles are pretty big, so we may have some kind of discontinuities between them, as essentially we are sharply switching from one light list into another. In order to hide those, we are using a stochastic bilinear lookup. And obviously, we can't just sample the visible light list. The scenes are dynamic, and lights which were hidden now may become visible. So what we do here is that we allocate 20% of our samples towards checking hidden lights. And this can be pretty simply implemented by separately sampling hidden light list and separately sampling visible light list. And just before we merge them, we can clamp the weight of the hidden light sample to the 20% of the total. And this works much better than, for example, downweighting the hidden lights. As now we can guarantee that even if we have this very strong occluded light, we won't ever send more than 20% of samples towards it. And if the history reprojection fails, for example, after reprojection will be out of screen bounds, or maybe the depth test will fail, we still want to use our closest visible light list, as most likely contains some good lights. But we are going to increase the hidden light fraction to 50%. So this way we can speed up the visible light discovery. And now, when we have this visible light list, we can take a look at our new pipeline. It looks pretty similar to what we saw before, but now we have this new orange block. This block is responsible for building the visible light list per 8 by 8 screen space tile. And later, we can use this list in order to guide our samples. Building the list is pretty cheap. Most of our traces contribute towards the final pixels. And also, we have this light list, which we can use now to generate those nice patterns for the denoiser. In order to select our samples, we use weighted reservoir sampling. You can see it here at the bottom. It's a very simple algorithm which allows us to loop over all lights once and stochastically select one based on their weight. We weight each light by the luminance of a brdf, and we also apply a logarithm for perceptual weighting. The idea here is, for example, if we have a very, very strong light, then after tone mapping, it won't really affect the final pixels as much. And for those nice patterns optimized for denoising, we are going to use spatial temporal blue noise. Now, there's one problem. So STBN precalculates a single random variable per pixel. But as you can see here at the bottom, we actually need a bunch of those random variables just to select one light per pixel. Thankfully, there are some ways which can allow us to reuse this random variable multiple times while still preserving those nice STBN noise properties. In order to pick one sample per pixel, after each light selection loop iteration, we can warp the selected range back to 0, 1. And if we want to trace multiple pixels, multiple rays per pixel, then we can use dittered sampling, which essentially will just remap our random variable into multiple segments. And all of this allows us to sample all the lights using just a single random variable. But the most important part here is that we manage to maintain those nice STBN noise properties. So we get this really nice quality increase essentially for free. We don't really do any extra computations. We don't trace any extra rays. Now we know how to select a light, but in a real scene, we cannot be really looping over all lights inside the light grid cell. There may be like hundreds of those. So what we do instead is that we check all the lights on the visible light list. Most likely they will be still visible. And we check some lights from the light grid cell, where each pixel checks a different subset. This is pretty incoherent and not great for performance, but it allows us very quickly to discover new visible lights. Another small optimization which we do here is because we weight each light by the luminance of a brdf, we don't really need to compute the full RGB. We can just scalarize our computations and save some VGPRs. And we also drop samples below a certain threshold. This is not really a performance optimization, but it helps with quality. The idea here is if we have a light which isn't really strong enough to affect the final pixel, then there's no really point to check its visibility. Instead, we should use this ray for something more important. And light weights are usually pretty similar between pixels, at least if depths and normals are similar. So we can use this in order to sample at a lower resolution. For example, instead of selecting 1 light per pixel, we could be selecting 4 lights every 4 pixels. The important thing is that we need to be really careful with our sampling patterns. We use either checkerboarding or Forux pattern, and we jitter those patterns both in space and in time. This way, we can maximize our chances to be able to reconstruct something. For the actual reconstruction, we use stochastic bilinear upsampling with some depth and normal weighting. And if we cannot reconstruct something this frame, then we are just going to reuse history without any kind of history rectification. So no neighborhood clamp or anything like that. And overall, this technique sometimes can make our shadows softer, but it also speeds up sampling 4 times. So usually it's a great trade-off in practice. Directional lights can be pretty tricky when using stochastic sampling because we weight each light by the brdf, and directional lights are usually thousands times stronger than any local lights. So we essentially may end up just tracing all rays towards the directional light. A pretty popular solution is just to remove directional lights from the stochastic light sampling and, let's say, run them in a separate ray tracing shadow pass. But it's also pretty expensive, because now we need to trace this extra ray per pixel, and we need another denoising pass. So what we do here instead is that we limit directional light samples to 50% of our budget. And we are going to relax this limit as the local lights are dim, or maybe there are no local lights at all. Basically, in that case, we still want to send all the traces towards the directional light. Another thing we need to take a look here are area lights. Those may be pretty big, and just binary visibility isn't really enough. For example, if we take a look at this screenshot here, a large part of this light is occluded, and we may end up just tracing a bunch of rays towards the occluded part, wasting our budget. So what we do here is that we have a special 2x2 bit mask, which tracks visible parts of each light. And this bit mask is just built together with a visible light list. And when we are sampling our lights, first we select 1 light per pixel, and then for each light, we need to select a specific point on the light source. And during this selection, we are going to downweight the hidden parts of the light. This way, we can send more rays towards the visible parts, reducing noise. And as before, we are going to use STBN with sample warping, just a bit different flavor of those, as now we're dealing with 2D points. And now we are ready to shade our samples. So first, we are going to accumulate all the visible samples which affect all the visible sample weights which affect given pixel. And then we are going to multiply this accumulated weight by the pre-integrated light irradiance. This does cut some corners, as basically pre-integrated light irradiance assumes that we can separate shading from shadowing, but it allows us to remove a bit of noise, and most importantly, it enables us backwards compatibility, as now stochastic lights will look exactly the same as non-stochastic ones. It's not really a fundamental limitation, just a certain trade-off which we made here. And after shading, we'll be doing denoising. Already, with just TSR, things look pretty good, but there are definitively some parts which would require dedicated denoising. We have a single denoising pass for all lights, and it runs on separate diffuse and specular signals. Both of those signals are demodulated, which means that we remove non-stochastic material properties. We don't want to be blurring things like, for example, texture albedo. And the general idea of a denoiser is based on tracking temporal variance, which was introduced by SVGF. So this temporal variance gives us an idea how noisy is a pixel, so we know how much of a spatial filter we need to apply to it. On the temporal filter side, this is where we reproject history, accumulate lighting, and lighting moments. We store our lighting in two 32-bit formats, which is possible thanks to stochastic float quantization. And we also store the first and second moments, but only for the luminance of diffuse and luminance of specular. And later we can use those moments to reconstruct temporal variance. We run our neighborhood clamp. It's a pretty wide clamp of 5 by 5. So first we load and pack everything into group shared. And then from this group shared we can run our variance clipping. There are two interesting tricks which we do here. So the first one is that we are going to reduce the history weight based on the distance from the neighborhood bounds. The idea here is if our new data is really far away from the history, then most likely we should discard this history really quickly in order to remove ghosting. And the other thing is when doing downsampling, some of our pixels are going to be reconstructed. So for those samples, we are going to relax our neighborhood clamp a bit. Spatial filter is a bit different from standard ones. We don't run those multiple true passes, because that's just too expensive in our use case. Instead, we have a single pass with a single sparse kernel, which is rotated per pixel. And this works pretty well with TSR, which can clean it up. And we only apply this kernel in pixels where we have a high relative variance. This not only improves performance, but it also helps us to make the signal a bit sharper. Then we do the standard edge stopping functions. We don't want to be blurring some unrelated materials. And in order to handle this occlusion, we are accumulating in tone map space, which allows us to remove fireflies. And we also increase the number of spatial samples. And as we accumulate more data into the history, we are going to fade out both the tone mapping and those extra samples. And there's one more issue with denoising which we have to discuss here. So denoising accumulates in render resolution, but the temporal upsampling accumulates in display resolution, which is much higher. What it means is that one pixel in our denoiser's history corresponds actually to a bunch of pixels after upsampling. So when doing denoising, we have this choice. Either we blend those unrelated pixels, which results in blurry lighting, or we have to discard history each frame, which basically results in noise. But as we could see before, often a large part of the energy just coming from one or maybe two lights. And let's say if 80% of the energy is coming from one light and we were able to sample that light this frame, then most likely this pixel isn't really noisy. And we could just pass it directly to TSR. And we have a pretty good heuristic for that. The visible light list gives us a total amount of energy which a pixel can receive. And we also know what we successfully sampled this frame. And now, based on this fraction of the sampled energy, we can either reduce denoising, or sometimes we can just pass the signal directly to TSR. This heuristic itself may be a bit noisy, so we apply a bit of temporal stabilization on top, but overall it works pretty well. I'm not sure if it's visible here, but this image on the right is much, much sharper. And now I'm going to hand it off to Tiago.
Hi, everyone. Let's now go over how we actually compute visibility for the light samples. The main method we use is hardware ray tracing, which allows us to avoid the overhead of maintaining and rendering multiple shadow maps per frame, which is especially problematic when dealing with large numbers of lights. However, while shadow quality is extremely important here, we can't represent all objects in BVHs with the amount of detail that is used to render the main view. First of all, there's a high memory overhead per vertex. And in Unreal games using nanite that tend to use highly detailed meshes, that means that BVH builds and tracing can become too expensive. And on top of that, kit-bashed environments result in a lot of instance overlap, which further increases the tracing costs. So instead, we need to use simplified proxy meshes, as well as aggressive instance culling and aggregate representations to reduce the complexity of the levels in ray tracing. We use two ray tracing representations of the levels. In the near field, which covers an area of 150 meters around the player camera, we use proxy meshes. These are lower polygon representations of the original geometry that provide a good balance between performance and accuracy, and are ideal for close proximity tracing. If rays don't hit any near-field mesh and extend outside its radius, we also trace against a more aggressively simplified representation of the level, and in this representation, we merge instances and significantly reduce triangle count to keep ray traversal costs down. The far-field representation is stored in a separate TLS, which makes those traces faster since the BVH complexity is far lower. And use inline ray tracing by default, since we get better performance on the current generation of consoles. Using proxy meshes for ray tracing has one major downside, which is mismatches between the proxy geometry and the rasterized geometry. Those mismatches cause incorrect self-shadowing, since the rays are traced from the rasterized geometry surface, and they might immediately intersect with the proxy mesh triangles. In these screenshots, we can see incorrect shadowing on the wall in front of the player, because that mesh uses tessellation that we can't efficiently represent in ray tracing. And similarly on the floor, there are mismatches that cause more self-shadowing, and even on the player character, there's simulated cloth mesh that is not well represented in ray tracing and results in an incorrect shadow. There are also the usual issues with animated and alpha mask geometry, which are especially expensive to represent in ray tracing and expensive to trace rays against. Unfortunately, these mismatch issues cannot be avoided by simply using front or back face culling on the rays. In the diagram on the left, we can see that back face culling is enough to prevent incorrect occlusion. However, on the right, we can see a situation where the ray also hits a front face, and in this case, it would result in an incorrect shadow. On top of that, we have found that using either front or back face culling adds about 10% of overhead tracing, since it prevents some early exits during the ray traversal. So all of this means that we cannot just rely on hardware ray tracing and proxy meshes, and instead we need to use fallback mechanisms to work around these issues. So the main method that we use to avoid this incorrect self-shadowing is to use screen space ray tracing. Since the screen rays are traced against the rasterized geometry depth buffer, we can rely on them to move away from surfaces without incorrectly intersecting the proxy geometry. And we can then offset the origin of the world trace based on how far the screen trace got, similar to what the diagram shows, which avoids most of the self-shadowing issues. And of course, another benefit is that we get contact shadows with detail that is not represented in the BVHs. However, unlike typical contact shadows, where we can usually get away with a small number of taps and short ray length, we need our screen traces to be pixel accurate. Otherwise, we might skip over occluders. And the ray length is defined in world space, which means that in some cases, we need to trace the rays all the way across the screen, which is too expensive to do with fixed stepping. So to address this, we rely on HDB tracing to be able to quickly but accurately skip empty space without testing against every pixel along the ray. We want to avoid typical screen space artifacts as much as possible, so we assume a very conservative low surface thickness by default, meaning that in most cases, we fall back to hardware ray tracing when rays go behind surfaces, instead of assuming that there was an intersection. Another issue is that long screen traces cause noticeable artifacts due to depth buffer aliasing. So in practice, we limit the length of the ray to avoid those issues. And tracing against the depth buffer can cause its own self-shadowing issues, which we avoid by combining both point and bilinear sample depth. We also track whether instances are represented in ray tracing using a stencil bit. And if the ray goes behind one of those pixels, we increase the estimated thickness to get a bit more contact shadows from those instances. Now let's talk about alpha mask geometry. While for diffuse GI, we can usually get away with tricks like shrinking or culling triangles during the BVH build based on the alpha mask to cheaply approximate occlusion, Those methods don't work well for direct shadows. Ideally, we would support some sort of fixed function alpha masking that we could directly evaluate when using inline ray tracing. But since artists are able to define the alpha mask using material graphs, that's not really practical for us. So we're left with a few other options. We can trace all rays using full any hit evaluation, which gives us accurate results, but on the other hand, we can't benefit from inline ray tracing, so it adds a lot of overhead on consoles. The second approach is to do the usual lightweight inline trace first, and if we hit an instance that needs material evaluation, we trace a continuation ray with any hit evaluation enabled. This approach gives us accuracy where needed, but without losing the inline ray tracing benefits for all rays. There are still situations and content that makes hardware ray tracing simply not practical on current-gen hardware. The overhead of running any hit shader might simply be too high, especially since it's usually used on dense foliage with lots of overlapping triangles. Or there might be heavily instanced animated meshes, which require a lot of memory and time spent building BVHs. To work around this, we also support falling back to virtual shadow maps instead of using hardware ray tracing for specific lights. Virtual shadow maps support features that are useful for our purposes. They're capable of generating plausible soft shadows, so they mix well with other hardware ray traced shadows from other lights. And during the light sampling pass, we can also mark which pages are sampled to avoid the necessary work rendering meshes into the shadow maps. This fallback method doesn't need to be a binary choice. We allow artists to manually tag which instances should be rendered into shadow maps and still rely on hardware ray tracing for instances that are well represented in ray tracing. However, it's important to note that this fallback option doesn't address the fundamental shadow map scaling issues. So in practice, this is mostly used for the directional light, since representation mismatches tend to be more noticeable for those lights. Putting it all together in this diagram, the core of our ray tracing pipeline consists of screen traces to avoid incorrect self-shadowing, followed by near-field traces, which handle most of the rays. If the ray hits an object that uses alpha-masked material, we have the option to retrace the ray with material evaluation. Similarly, if the ray extends past the near-field radius, we trace against the far-field representation of the level. And finally, for lights that use VSM, we also sampled shadow map. Register pressure and occupancy is also something we need to consider in our shaders, since they need to handle a bunch of material types and light features. To address this, we run tile classification based on both material type and also the types of lights that affect each tile, so that we only have to pay for the worst case VGPR usage where it's actually necessary. In particular, the logic to support rect and textured lights add quite a bit of overhead, so we have specific shader permutations for those. In the Megalights demo, doing this extra classification based on light types improved the occupancy by around 20% with little overhead. So this wraps up our opaque pipeline, so let's move on to translucency and volumetric fog. For context, in UE, we calculate and store line for volumetrics in two structures. For volumetric fog, we use a camera-aligned froxel grid, and for particle effects and other translucency, we have a world space grid around the camera where we store first-order spherical harmonics per voxel. These structures are updated every frame by injecting lights into them, and shadowing is typically calculated using shadow maps. However, with Megalights, we don't have shadow maps, and injecting so many lights is also very expensive. So these structures had to be upgraded to integrate with Megalights. The general approach that we use for opaque pixels can also be applied to these volumes. We can run sampling at half res, peak and light samples per voxel. We then trace shadow rays, evaluate lighting for the visible samples using phase function for the volumetric fog and the diffuse brdf for translucency volume. And finally, we build visible light lists. And we have to do this twice, once for each volume. There are a few issues with this straightforward approach. First of all, the probes are quite sparse, especially for the world space grid. So gathering visibility from nearby voxels tends to lead to ineffective guiding in areas with high-frequency shadowing. And secondly, there's a lot of duplicate work between the two volumes. We are picking important lights and tracing shadow rays from a bunch of probes in the world, but as you can see in the screenshots, the coverage of the probes for those two volumes can overlap significantly. leading to duplicate work. One idea is to simply extend the froxel grid structure to also store spherical harmonics and use that to calculate lighting on particle effects and translucent objects. This seems like an efficient way to avoid duplicate work between the two volumes and improve guiding effectiveness on translucency, since the froxels are denser. However, in practice, this causes a few noticeable visual artifacts. First of all, the underlying structure of the froxel grid is quite noticeable, especially when the camera moves. This sort of issue can also happen with world space grid, but at least it's not, in that case it's stable since it's not camera dependent. And we also need to use temporal filtering, but reprojection causes noticeable issues that we cannot completely avoid. Another option is to use a hybrid solution, where only sampling and tracing are shared between the two volumes. We run sampling logic for probes based on the froxel positions, since they're denser, which means that we can share visibility data between neighbor probes without hurting guiding effectiveness. We then run tracing for those samples. And finally, we run two shading samples, one for each volume, where each volume stochastically gathers samples from the closest sampling probes. Earlier, when we talked about the opaque pipeline, we mentioned the assumption that typically 80% of the energy comes from one light. While for opaque surfaces, we have access to the normal and material properties that we use during shading, during sampling, we can get away with a few samples per pixel. Selecting samples for translucency is more challenging. First of all, we are injecting the lights into spherical harmonics, and we don't know which surfaces will be shaded using each voxel ahead of time. The froxels are still quite large relative to pixel size, so stochastic upsampling from neighboring voxels can lead to instability or require wider filtering. And since sampling is done in a unified volume, we have to consider both the phase function and the translucent brdf, which causes light weights to be more uniform. And the combination of these factors means that we end up having to shade more samples per voxel than are usually required for opaque surfaces. We can do this easily by increasing the number of samples per voxel, but of course this makes all stages of the pipeline more expensive. Alternatively, we can extend the stochastic upsampling that we do during shading, and instead of shading samples from a single neighbor, we can gather, combine, and shade samples from multiple neighbors. This avoids extra sampling and tracing overhead, but also results in a loss of lighting detail since it ends up blurring the visibility term. Finally, we also apply temporal and spatial filtering to improve lighting stability in the volumes. Some translucency, such as glass, requires higher quality lighting and including specular. A simple approach is to consider the front layer to be the most important and shade it by running the whole Megalights pipeline again, so it gets accurate lighting. However, this is usually too expensive in practice, since we can easily end up doubling the overall cost of lighting if the player gets too close to surfaces. We also need to support shading multiple layers, so we need to handle this in a more scalable way. One cheap option is to light these surfaces using the translucency volume. We can double down on the spherical harmonics that we already have and extract the dominant direction to approximate specular lighting. This approach can work well in simple cases, but as you can see in these screenshots, it can only support one specular highlight and requires lighting in the spherical harmonics to be very stable. Otherwise, specular can noticeably jitter, even when the lights are static. For now, we are using this method, but this is an area of ongoing work since we want to support better lighting quality on this type of translucent surfaces. So let's now take a look at all this comes together in terms of runtime performance. These numbers are from the Megalights demo running on a PlayStation 5 at 1080p render resolution with one sample per pixel and async compute disabled. There are over 900 lights on screen, which result in around 20 to 80 lights per pixel. And the total cost is about 5 milliseconds and a half, and that covers all the shadowing and shading costs for direct lighting. One interesting thing to note is that sampling for opaque surfaces takes more time than shading, despite running at half resolution. That's because sampling cost scales with the number of lights, which is very high in this scene. And a lot of those lights are rect lights, which, like I mentioned earlier, are very expensive to sample and limit occupancy. On the other hand, shading has a more fixed cost, since it has an upper bound on how many samples are shaded per pixel, making it relatively stable, since the cost is only really affected by the tile type. Another thing to notice is that translucency shading is almost as expensive as opaque, despite there being significantly fewer probes than there are pixels on the screen. That's because, as we discussed earlier, translucency requires us to shade more samples per voxel in order to improve stability and reduce noise. Overall, once artists start using Megalights, it quickly becomes clear how much fun they're having. It was really interesting to see the progression as they got into a new mindset while working on the Megalights demo. They started slowly, putting lights here and there, but that quickly changed, and we started to see many more lights in the level. Then, as you can see in these screenshots, we also started to see the usage of rect lights ramp up. And at some point, artists got really comfortable using tools like procedural light spawners to automatically place lights along splines. The entire system scales much better and is more forgiving, but content optimizations like reducing attenuation range, cone angles, or barn doors are still useful to reduce noise and the sampling pass cost. To wrap things up, Megalights leverages real-time ray tracing to evaluate direct lighting even on current-gen consoles. But of course, there are still quality limitations, such as how well meshes are represented in ray tracing, and in most cases, we are limited to one sample per pixel, so careful sampling and denoising are critical. The performance of this technique scales with number of light samples per pixel and the ray tracing scene complexity. And overall, we have found that this is a good trade-off in practice, and that light counts aren't a major limitation anymore. In terms of future work, we are still working towards making Megalights production ready. There's a bunch of optimizations, fixes, and missing features that we need to implement and improve. Scalability is still an open problem. Once content is authored using Megalights, it becomes challenging to reduce light count without requiring a lot of work from lighting artists. And we don't want to end up in a situation where artists have to maintain multiple lighting setups manually. One of the most important areas is denoising and upsampling. At the moment, Megalights runs its own denoising, and then the output is further processed by TSR. There's a ton of new research using machine learning that shows very promising results in this area. And we think that there's opportunity here to unify and, in general, better integrate these passes to reduce costs and improve final image quality. And the main challenge for the future is mesh representation in hardware ray tracing. Until now, we have been sort of able to get away with low-poly proxies and other shortcuts, since diffuse GI and rough reflections are quite forgiving. But shadows for direct lighting can easily expose the underlying representation of the meshes. Dynamic geometry is still very much an unsolved problem, and it can easily blow memory and performance budgets, making it currently impossible to accurately represent large numbers of animated instances. And while we are starting to see new extensions to ray tracing APIs that will enable more efficient representation of nanite meshes, geometry complexity is constantly growing, and there are new types of content that are even more challenging to represent in ray tracing and will need to be addressed. So that's it for our presentation. We would like to thank everyone that helped with the slides, the UE5 team, the artists that worked on the Megalights demo, and Natasha for organizing the discourse. Thank you.
So we have a few questions, and we have a bit of time, so we actually could ask them. First question from Melino Conte. Have you looked into many light merging techniques like light cuts?
Yes, I mentioned those in the beginning as those light hierarchies. And essentially, the main problem which we have here are those like occluded lights. And they don't really help much with that.
Next question from Matthew Gomez. How do you determine if upscaling has failed for a given frame before you fall back to last frame's information?
So when we are doing upscaling, we weight each pixel by the depth and normal, and if those weights are 0, then we just cannot upscale. Let's say there's like a very thin wire or something like that.
Next question from Stephen Hill. Have you run into precision issues from multiple rounds of sample warping from the same blue noise sample?
Yes, that's a great question. Yes, each time we warp that sample, we are losing one bit of precision, but we are not really sampling that many lights. As I talked about that in the next slide after that, we try to sample like a small amount of lights because we only sample the lights which were visible last frame, and we only sample like a few lights from the light grid cell. So overall, we don't run out of those bits.
Next question from Sergei Kulikov. Using only ray tracing to check light occlusion should require high-quality ray tracing geometry, ideally matching rasterized view. How well does it work with, let's say, animated nanite meshes? Unless I've misunderstood and some other shadow technique accompanies RT occlusion checks.
Yeah, so in some cases we do support, we can support animated proxy meshes. That will cause mismatches, and screen traces do tend to work very well. Another thing that we've noticed is when we have megalights, artists end up placing a lot of soft lights or lights casting soft shadows, and that does help hide the mismatch issues. And finally, we have the virtual shadow map path for like hero lights, or in situations where this is really a problem, they can mark those specific instances to be rendered into shadow maps, so then they get the full accurate shadow representation. Yeah.
Next question from Kierwood Gilbert. Are there strategies to reduce latency of disocclusion detection? Is any filtering applied to hide sudden luminance changes in those cases?
Yes, we do have this disocclusion filter, which is basically just like some extra spatial samples applied to frames which didn't accumulate enough history. And overall, the latency is mostly good because of this shading confidence thingy, which fixes most of the stuff. And it's only a problem when there are really a lot of lights, so we are not able to accumulate them quickly.
Okay, we'll do two more questions, and then there will be loads more in Discord. Jordan Robinson asks, could you get rid of proxy meshes with cluster acceleration structures?
Yeah, so yeah, this is definitely something that we're interested in. It's not currently possible on consoles, so we cannot really do it. But yeah, it's something we'll definitely integrate. It's unclear if we can completely get rid of proxy meshes. Stuff like tessellation and if you've seen nanite foliage is not really something that we can represent even with the current, with the new ray tracing extensions. But yeah, ideally we would be able to get rid of all proxy meshes and screen traces, but we're still far away.
Last question from Peter Sikachov. How well do megalights work with moving lights, fast-moving camera, for example, driving, and animated meshes?
Yes, so again, this depends on how complex is the lighting at a given pixel. If, for example, there's only one dominant light, or maybe two, then they handle it pretty well. But if there's, for example, like 20 lights, which require multiple frames of accumulation, then it's really bad. So it's hard to answer this question. But basically, stochastic sampling gives you this slider where you can slide between performance and quality and those temporal issues. And it depends, how do you want to set it up.
Super. Thank you very much for both a really exciting talk and fantastic answers.